So our next speaker is Josh from ISA Pune. He's a second year MSc student there. And Josh will be speaking on Burnside's theorem on matrix algebras.
So my topic is Burnside's theorem on matrix algebras, and the plan for this talk is that I will start with defining some basic things about algebras because it might be a new concept to some people, and then we state finally what Burnside's theorem is, and eventually move to a proof of that. So first of all, the first introduce is what a K-algebra is. So K-algebra is basically a vector space, but there's this additional facility now to multiply any vectors as well. So that's the formal definition that I've written out there, that it's a K-algebra comes with three operations. One is plus, a dot from the K that you're considering, from the ground field, and a star, which is the facility to multiply vectors basically. And the other important condition is this new operation star that we are considering. This is well behaved with respect to the originally existing operations on that set. So I've formally written out what that means in the second axiom that I've stated here. That is, it distributes over plus or from both sides, as well as it has some sort of associativity to it. I won't spend a lot of time on these definitions because I eventually want to get to Burnside's theorem. But I think it would be good to have some ideas, some examples in mind of algebras. The first algebra that one can think of is perhaps the ground field K itself. We know that any field over itself is a vector space. So the first condition is satisfied. That is, K with plus and dot would be a K vector space. And since it's a field, you also have a operation to multiply elements in it. So you also have another operation star, which behaves well with the other operation. For the rest of the talk, the main example that we'll be considering is MNC, which is an algebra. We know that matrices form a K vector space. Matrices over C form a C vector space in particular. And you can also multiply matrices with each other in such a way that it behaves well with the plus and the scalar multiplication of. So let me just put that these two examples there. And for most of the talk, these are perhaps the only examples that we shall deal with. So the first example that we saw was K itself. And the second example is n cross n matrices over C. So whenever we see a new algebraic structure, one of the first things that we see is we see substructures of that. That is, we see these subsets of that structure, which when with the induced operations by themselves preserve the structure. We do the same thing here as well. So you have an algebra, we look at a special subset. If that subset with these induced operations is again an algebra by itself, then that is a sub-algebra. So in particular, one can get, so usually that's not the definition that we work with though. We obtain some condition to check that, for example, if you have a vector space, we try to get a condition to check whether W is a subspace of V. Or if you have a group, we want a condition to check that H is a subgroup of G. So similarly for a sub-algebra also, you can have a condition, which is what I've listed out. I wouldn't prove this right now, but it's easy to check. So if you have a subset D in A, we say that it's a sub-algebra if two things happen. Firstly, the vector space structure itself needs to be preserved. So the first requirement is that D should be a vector subspace of A. And secondly, it should be closed under this new operation which allows me to multiply vectors in it. So now we move our attention back to matrix algebras since we want to mainly talk about them. So now any matrix represents a linear map from V to V. So in particular, when you do a linear algebra course, we come across this definition of invariant subspaces. An invariant subspace for a linear operator is carried to itself under that linear map. So that's what I've written out over here. So if you have a linear map from V to V, I say a subspace W in V is invariant if T maps that subspace into itself. So some of the obvious examples which first come to mind are for any linear operator, we have these trivial invariant subspaces. That is the zero subspace. We know that any linear map carries the zero element to itself. So in particular, it's carrying the zero subspace inside the zero subspace. So the zero subspace is T invariant. The other one is of course a full space. We know that V would, since the map is from V to V would be carried to itself. So for any linear map, you can associate these trivial subspaces as invariant subspaces under that map. So we try to extend this definition first before we make a couple of other definitions. That is, now instead of looking at one operator, I'm looking at a collection of linear operators. So let's say I have a set of linear operators. So all these linear operators now are going to be maps from the vector space to itself. When do you think I will say that a subspace W in V is going to be invariant under this collection? What is the obvious and natural definition that you think would work here? Yeah, so I should perhaps write out the setup that I'm talking of. So this collection F has some linear operators. So every element F in this collection script F is going to be a linear map from V to V. So now I fix a subspace W in V. The question is, when do you think I will say W is invariant under this collection? The idea
if W is invariant under every element of that set.
That's correct. Yeah. So that's the definition that we go with. So we say that a subspace W in V is going to be F invariant under script F if W is little f invariant for each f in script f. Right. So now, before we go further, so if I give you any collection of linear operators, we just saw earlier that for any linear operator, zero subspace and the full space are always going to be invariant under that linear operator. So if I give you any subcollection of linear operator, I can always associate these same two subspaces for sure as being invariant under that collection as well. Because we know every operator would preserve these subspaces, the zero subspace and the full space. So there are always these trivial candidates even over here, even for a collection. That is 0 and the full space V are going to be F invariant for any subcollection F of linear operators. So we look at these special subalgebras now. So if I have, so the algebra that I'm considering is matrices over C. So if I have a subalgebra of the matrix, right, I say it's irreducible if the only invariant subspaces are in fact these trivial ones. That is the zero subspace and the full subspace. Right. So the first thing we do is, now I think we have enough tools to actually say what the Burnside's theorem states. So Burnside's theorem tells us that in this matrix algebra that I'm considering, the only irreducible subalgebra that I have is going to be the full space MNC. So the first thing that we do is we transform this definition of irreducible subalgebras in something easier to work with. And we make a definition called transitive subalgebras. So if we have a subalgebra, we say that that subalgebra is transitive if for any non-zero vector, A times B, which is the collection of all vectors that you get when the algebra acts on that, is going to be the full space. People who have seen group actions might be able to relate this with the notion of a transitive group actions. However, I would like to clarify that this is not essentially the same, because the normal group action that you see is of GL and C, the general linear group acting on the vector space. In this case, the algebra that you're considering under the star operation need not be a group. So it's not really a group action in strict sense of word, but sure, the definition certainly looks similar. So the idea is that any irreducible subalgebra, that is any subalgebra which would only preserve the trivial subspaces, would in fact be transitive. That is what we first proved. And then in order to prove the Burnside theorem, as long as we are concerned, we will usually work with this definition of a subalgebra being transitive. Yeah, so that's the first proposition that I make. That is, if I have a irreducible algebra of linear operators, then that algebra should be transitive as well. Right. So what we need to show is, given any non-zero vector, I should be able to show that A times V, script A times V, which is the collection of all A dot V, should be the full space. So there are two things to note first. We firstly observe that this script A times V is going to be a subset of V, but more so, it is going to be a special subset. In fact, this subset, I will show that is in fact A invariant. Then, given that A is an irreducible subalgebra, that gives me only two options for the subalgebra. That is, it should be it should either be just 0, or it should be the whole vector space V. So let's do that first. We first show that script A times V is not just any subset of the vector space. In fact, it is going to be a vector subspace. This can be verified quickly. The two things that you check for something to be a subspace is that it should be closed under plus and it should be closed under multiplying with scalars. So if I take any two vectors from script A times V, that's going to look like A1 times V plus A2 times V for some A1 and A2 in the algebra. If I add them, so if I add them, then that's what I get, because we have this this dot which is behaving nicely with plus and so on. And the algebra is a vector space. So in particular, it's going to be closed under plus. So A1 plus A2 is going to again belong to the algebra. So this plus, that is the addition of any two vectors from script A times V, is again going to land inside the algebra. The other thing we need to check is it being closed under multiplying with scalars. That's again a simple check. Again follows from the fact that script A is a vector subspace. You take any vector from script A times V, that's going to be A1V for some A1 inside script A. Again use the fact that script A is a vector space. In particular, it's going to be closed under multiplying with scalars. So this new operator that I get here, alpha times A1, this is again going to land inside the algebra, which tells me that script A times V is going to be a vector subspace of V. The second claim that I made was that script A times V is in fact going to be invariant under script A. So for that, I need to show that script A of V is going to map any vector inside it to itself. So I pick any vector in script A times V, that's going to look like A times V for some A inside V. So now if I take any member of the algebra and multiply it by it, that is, I'm taking any B in the algebra, I multiply B with that vector that I started with. I again use the fact that since A is algebra, the scalar multiplication as well as the star map that I have, that is multiplication of vectors map, that behaves well with each other. So I can write it in this way. Now B is from the algebra, A is from the algebra, which implies that B dot A is from the algebra. And that implies that this whole thing again belongs inside the script A times V. So that shows that script A times V is in fact an invariant subspace, and I'm working in an irreducible algebra. So I know that the only invariant subspaces in this case are going to be the trivial ones. So that gives me two options. Either script A times V is going to be 0, or script A times V is going to be the full space. By the way, there was this little convention that I follow for the rest of the talk. I think I forgot to mention it at the start. Whenever I talk about a subalgebra, we shall only deal with non-trivial subalgebras in this case. So in particular, I do not consider 0 to be a subalgebra. Of course, it satisfies all the conditions, but it just makes the notation simpler. which is what we shall observe even through the course of this proof. So two things might happen. One is script A times V might be the trivial subspace 0, or it might be the full space V. I eventually started off to prove that A times V should be the whole space V. So I should show that this case, in fact, can never occur. So let's see what happens if this is actually true. That is, what happens if this case, which I do not want to happen, actually happens. So in this case, script A times V is 0, which means that this vector V is going to be killed by every member of the algebra. In particular, that vector V will be in the kernel of every member of the algebra. That's exactly what I say here. And we know that this thing, one can check, is in fact an A invariant subspace. Again, you need to just proceed by definition. You take a vector V in this, that is going to be killed by every A in every A inside the algebra because it's in the kernel, and you show that its image under any element will also in fact be killed. So this is a non-zero invariant subspace. It's non-zero because we had it's non-zero because we had started with a non-zero vector to begin with, and we have this non-zero vector V inside this intersection. So in particular, this is a non-zero A invariant subspace. So it must be the full space because the algebra that I'm considering is irreducible. So what does that imply? That means that in particular, the full space V is going to be a subset of the intersection of all the kernels. That means for every V in V and for every A in the algebra, V belongs to the kernel of A. That would imply that in fact the algebra itself is trivial, and by the initial assumption that we made that this whole talk is just mostly about non-trivial subalgebras, we get a contradiction because every subalgebra that I'm considering is always non-trivial. So as a result, the other case must be true, and script A times V is going to be the full space V. So that tells us that any irreducible subalgebra is in fact also going to be transitive. The other direction is also in fact true in this case. However, I wouldn't be needing it for the rest of the proof, so I wouldn't be proving it here. But that is also a simple check, and I leave that as an exercise. That is, given any transitive subalgebra, you can show that that would also in fact be irreducible. So now we can finally move to Burnside's theorem. That is, if I'm given any irreducible subalgebra in MNC, then that irreducible subalgebra should in fact be all of MNC. So the reason why we developed all of this machinery is because now henceforth, whenever I need to use, whenever I talk about irreducible subalgebra, I shall in fact use the fact that it is even transitive and use the properties of transitive. Proof proceeds is if you have a vector subspace like V, then it's enough to show sometimes that the generators are all there in that subspace if you want to show that that subspace is going to be the full space V. That is exactly what we do. Given any irreducible algebra, we'll show that it contains all the rank 1 matrices. Now, any linear operator can be written as a sum of rank 1 matrices by doing this. That's what I've spelled out over here. So, if I have any linear map, I use linear map and matrix synonymously because you can identify them with each other. So, if I take A equals Aij, I can write A as summation of Aij times Eij, where Eij is this elementary matrix with only 1 at the ijth position and 0 everywhere else. And then since A is a matrix algebra, it's closed under plus, and I will be able to show that everything is in fact in there. So it suffices to show that all the rank 1 matrices are in fact in the algebra A that I'm considering. So I proceed by following 2 steps. The first thing that I show is that any irreducible subalgebra at least contains one rank 1 matrix, and I will use that rank 1 matrix then to prove that it should contain in fact all of the rank 1 matrices. Right. So again, we draw parallels with perhaps the proofs that we have seen before. we want to get hold of a rank 1 matrix inside the algebra. So people who have done group theory before will perhaps know this proof of how do you show if you have a cyclic group, every subgroup of that should also be cyclic. In proofs like that, you need a candidate for the generator of that subgroup. And what you do is you take the element with the least order. I do something similar here. I have an algebra, irreducible algebra, and I want to produce one rank 1 matrix. So I look at the a non-zero a matrix which will have the minimal non-zero rank. Two reasons why this would be true. Firstly, I will get non-zero rank matrices because again of our initial assumption, the subalgebras that I'm considering throughout are non-zero subalgebras. So in particular, it will contain a non-zero operator. And a non-zero operator would have a strictly positive rank. So I pick that matrix which has a minimal non-zero rank, and I claim that that matrix would in fact have rank exactly 1 in an irreducible subalgebra. So what if that does not have rank 1? So that is, what if that minimal non-zero rank matrix that I'm considering has a strictly greater than 1 rank? In that case, I know that the image space is at least going to be spanned by 2 vectors. Sorry, not spanned by 2 vectors, but the image space is at least going to be 2-dimensional. So I would be able to find 2 linearly independent vectors in the image space. So that's what I write here. So I will be able to find 2 A1 and AV1 and AV2, which are linearly independent in the image.
Yeah, just why the image space will have at least dimension 2?
Because I'm proving by contradiction. I want to show that this minimal rank, the minimal rank matrix that I have picked is a rank 1 matrix. So suppose it's not of rank 1, then it should have rank at least at least 2. So in that case, it's at least 2-dimensional. So I will at least get 2 linearly independent vectors over there. So that's what I write here.
Yeah, okay.
So I'll be able to find an AV1 and AV2, which are linearly independent in the image. Now we use so as I had promised earlier that we will always henceforth use the transitivity in place of the irreducibility. So we know that the algebra is transitive now. So in particular, for this vector AV1, I will be able to find a member of the subalgebra which carries it to V2. That's what I do here. So the idea is I want to get some sort of relation for AV1 and AV2 in terms of the members of the algebra inter. So that gives me this. If I multiply both sides by A, I get AV1 is equal to AV2. Now we further know that these AV1 and AV2 are linearly independent. When do you say that 2 vectors in a vector space are going to be linearly independent? For 2 vectors, the condition is much simpler. We should just ensure that one should not be a scalar multiple of each other. So in linear independence of these 2 vectors that I'm considering, AV1 and AV2, implies that for every member of the ground field, this combination will be non-zero. Because if it is 0, then I would get a linear dependence relation between them. So I just rearrange that accordingly, and I can write that this AV1, the vector AV1, when multiplied by AB minus KI is always going to be non-zero. So now another quick observation that we can make is that these operators, namely for any scalar K in the ground field, AB minus KI and AB, these are both going to be invariant. So image of A is always going to be invariant under both of these operators. Again, something easy to check. You take something in the image space that is going to look like A times V. If I multiply this by A times V, I can again rearrange this and I get A times BAV. So I'm again landing up in the image. I leave it to you all to check that in fact, this operator AB minus KI that I am considering is also going to be have image of A as an invariant subspace. So in particular, the nice thing about invariant subspaces is whenever I have a linear operator between 2 vector spaces, and if I get an invariant subspace in them, then I can restrict my linear operator to this invariant subspace, and it will again be a linear operator because I know W will still map inside W. So in particular, I can treat this AB minus KI and that AB that I considered as now non-zero linear operators on the image space, because we just observed that image space is invariant under both of these operators. We further are working with a nice algebraically closed field. So we know that every polynomial has a root. So in particular, if I look at this operator, AB on the image space, so technically I should be using restrictions or something over here, but by abuse of notation, I called it the same. I call AB minus KI. You should now think of it as an operator on the image space. Similarly, even AB, when I treat it, you should treat it as an operator on the image space now. Yeah, so since C is algebraically closed, I know that this AB will have an eigenvalue. That means AB minus lambda I is not going to be invertible. When I view it as an operator now on the image space, that means that the rank of this operator is going to be strictly less than the dimension of the image space, which is exactly rank A. So the contradiction that I'm actually looking for is, we had started with a matrix of the minimal rank, and we assume that if possible, let its rank be greater than 1. So because of that wrong assumption, the contradiction that I'm looking for is, I want to produce another member of the algebra which would have rank strictly less than the minimal rank one that I chose. So that element that I pick is this one, AB minus lambda I times A. So we know that the rank of product of two linear operators is going to be less than each one of them. So I have this, and that is in fact strictly less than rank of A. So now this thing is going to be a linear operator on the full space V, which is going to have non-zero rank and rank strictly less than that of A, which is a contradiction. This contradiction arises because I assume that the minimal rank matrix that I picked from the algebra had rank strictly greater than 1. So that initial assumption was wrong, and I'm guaranteed of at least one rank 1 matrix in this irreducible subalgebra that I'm considering. Right. So the next step of this proof.
Josh, why AB minus lambda I itself will not work?
Right. So the reason is, I also want this thing to be in the algebra A that I'm considering. If I look at AB minus lambda I know AB is in the subalgebra because A is in the subalgebra, B is in the subalgebra, but I do not know if the identity matrix is in the subalgebra. So that's problematic, which is why I do this. The idea is, when I multiply this out, what I'm going to get is ABA minus lambda A. Now here I know all these three are in the subalgebra, so their product is in the subalgebra. A is in the subalgebra, and so lambda A is going to be in the subalgebra. And then if I subtract all of them out, I'm still going to remain in the subalgebra, which is why I do that.
Yeah, like subalgebra will not be containing I, identity matrix.
No, the subalgebra need not contain the identity matrix.
Yeah. Okay. Proceed.
Right. Okay, so now we are guaranteed the existence of at least one rank 1 operator. We are going to use this one rank 1 operator to generate out every rank 1 operator inside the algebra. So we need some results before we move to this. That is, we need to we want to know the structure of rank 1 operators. So I claim that any rank 1 operator can, so we know that for any rank 1 operator, the image is always going to be one dimensional. So it's all going to be in the span of one vector, some fixed vector W. And these scalars would depend on the input vector. So I claim that this dependence that I have, this is again a linear map, and in fact a linear functional. So it's going to be a linear map from Cn to the ground field C. So let's make this more precise. So I have a linear operator T from Cn to Cn, and I know this is a rank 1 operator. In general, I'm trying to extract out the structure of these rank 1 operators. So I know that for any x in Cn, Tx is always going to be in the span of some fixed vector W. right? So Tx is always going to be some lambda x times w, where the scalar lambda x that I'm considering is going to depend on the input vector. And I claim that if you define a function f, let's say, from Cn to C, which takes in a vector x and sends it to the corresponding lambda x, then this function f is again linear, and in fact is a linear function. So this is again simple to prove. You just check that it behaves well with plus as well as with multiplying with scalars. I shall quickly sketch out a proof of why it behaves well with plus. The proof of why it behaves well with dot is similar. So if I consider f of x plus
George,
y.
it's almost time.
Oh, okay. So
How
I
much
guess then
time
maybe
you need? Yeah.
I would
Can you
need
quickly wrap
another.
up?
Yeah, I would need another 5-6 minutes perhaps.
Please, yeah.
Sure. Okay, so I leave this to you to check then that this would in fact be a functional that behaves well with plus and dot. Right. So in particular, we now have a better idea of what rank 1 operators in fact look like. So any rank 1 operator T is going to be some functional times a fixed vector. And by Rees representation theorem, we know that every functional also comes from a vector. So every rank 1 operator on Cn is going to be determined by two vectors. One is the vector v, which determines the functional, and the other one is the vector w, which determines the direction in which I'm going. So that is the notation that I henceforth fix. T is going to be bracket of v comma w, where this rank 1 operator is going to be like this. Tx is going to be x with v, and you take inner product of x with v. See how this how these rank 1 so there are two claims that I make. One is if I pre-compose any rank 1 operator with any operator, then I'm again going to get a rank 1 operator, which is going to be given by this. So again, you just check this for every member of Cn. So S composed with V comma W on X, by the way we defined it, is going to be this. VW is a map. This is my notation for the map rank 1 operator, which is going to act in this way. And when I act S on it, I know that this thing is going to be a scalar. So this thing comes out, and I have X with V acting on SW, which is precisely this by the earlier notation that we fixed. Then we also see what happens with rank 1 matrices when you post-compose them. So if I post-compose it with a linear operator, let's say S, then I have this. Again, you check. Yeah. So just by definition, the way we define the action of this rank 1 operator V comma W, you have this, and we have this notion of the adjoint of a linear transformation, which obeys this identity under the inner product. So one can show that any rank 1 operator, when post-composed, again gives you a rank 1 operator, which is determined by its adjoint. So now we finally finish the proof off by showing that the algebra contains all the rank 1 operators. So we know that we have at least one rank 1 operator, which I denote by this V0 comma W0. So if I'm given any rank 1 operator now, let's say V comma W, I know that the subalgebra A is transitive. So in particular, I have a method to go from W0 to V via a member of the subalgebra that I'm considering. So I have a linear map S inside the subalgebra such that that linear map would carry my W0 to W. So since we earlier showed that post-composing has got something to do with adjoints, if I can show that the transitivity of a subalgebra A implies the transitivity of its adjoint subalgebra, which is the collection of all its adjoints, then I have a way to travel from V0 to V also by a member of the algebra M. So I shall quickly sketch a proof of this, but let's quickly observe that once I have this, my proof is done, because I just pre-compose and post-compose by those members of the algebra that I'm considering, and that allows me to travel to any rank 1 operator that I'd started with, that is V comma W inside the algebra A. So the only thing that is left in this proof is now we want to show that if I start with an irreducible subalgebra, then it's adjoint subalgebra, which is a collection of all its adjoint. Firstly, one can check that that is a subalgebra in fact, and in fact that is also going to be irreducible. So the key observation to prove that is we need to check that if any subspace is going to be invariant under the algebra that I considered, then its orthogonal complement will be invariant under the adjoint subalgebra. So I sketch out a proof of that. So we want to show that given M is invariant under A, we want to show M perp is invariant under A star. So we start firstly with any operator from here. We want to show that it preserves M perp. So that's the claim. So A star should send M perp inside M. So you just work with so you just start with any member of M perp that's going to look like M tilde. We want to show that A star of M tilde again lands up inside M perp. To show that something is in M perp, we need to show that its inner product with any member of the algebra M, with any member of the subspace M that I'm considering is going to be 0. Again, so we check that. We know that this adjoint behaves well with this operation. That is, you can send it on the other side. And M was A invariant. So in particular, this is again going to land inside M. And M tilde was an M perp. So that gives us that the inner product is 0. I claim that the other direction proof follows similarly, because for the other direction proof, all that you do is you now treat this as your algebra and this as a subspace that you're considering. If I take star once again, I'm going to get the original algebra back. And if I take perp once again, I'm going to get the original subspace back. So we have that any subspace would be A invariant if and only if its orthogonal complement is invariant under the adjoint algebra. So if I start with an irreducible algebra, we know that its invariant subspaces are going to be only 0 and V. That means the invariant subspaces of its adjoint algebra are only going to be the orthogonal complements of this, which are again going to be 0 and V in fact. So yeah, that finishes the proof for that one little step that we used. That is, we use the transitivity of A star corresponding to the transitivity of A. Yeah, so there are a couple of applications to this as well, to finite group theory, as well as to Schur triangulation, which we do in linear algebra. However, I don't think I'll be able to give a proof for that. The reference that I used for this is Professor Kumaresan's article on the same topic. It does not have the application to Schur triangulation that I wanted to talk about, but there is an article by Rosenthal. I shall perhaps write it out in the chat and also in the YouTube video link whenever it will be uploaded. And you can refer to that to see how Burnside's theorem would be used to prove that given any matrix, you can find always an orthogonal basis, which such that that matrix with respect to the orthogonal basis would be in upper triangular form. Yeah, any questions?
All right. It seems there is no question. Thank you, Josh, for the very wonderful talk.